Hey guys, KF7IJZ here with another exciting amateur radio video. In front of us we see two Elecraft KX3s, two A123 systems, ALM 12V7 batteries, two power monitors, and a single heatsink. Today I'm here with KF5JNU and we are comparing the performance of the different installation methods of the Pro Audio Engineering PAE KX3 heatsink kit. For those of you who don't know, in the market, we've seen about 3 or 4 different heatsinks being manufactured from different folks. Because as wonderful as this radio is, one thing that I think Elecraft really missed out on is you give us a radio that has PSK built into it, or PSK31 built into it. I can send PSK31 with the CW paddles, but the radio gets hot. The oscillator drifts as the radio gets hot, and considering how small of a heatsink that you've given us, you haven't thermally bonded the PA transistors to the case. It's just a mechanical bonding. I can't run the full 10 watts reliably for digital modes, especially for things like JT65, where you have full duty cycle for a couple of minutes. So the marketplace has responded by creating these add-on heatsinks, and the one we're looking at today from Pro Audio Engineering is the one that, after the most research, was the most desirable. One thing that sets this one apart from others is they include instructions for 3 different ways of installing this on your radio. The first way involves simply removing the factory heatsink and attaching this replacement one. And the second way involves removing the factory heatsink, using thermal paste to bond to the new one. And then the third way involves actually opening up your radio, thermally bonding the PA transistors to the case, actually removing the coating from the outside case, and then thermally bonding the heatsink to the case itself, which would in theory be the most effective. On the left, the KX3 from KF5JNU has been done with what we assume will be the best installation. He has thermally bonded his PA transistors to the radio case. He used a bench grinder to remove the coating on the outside in order to mount the heatsink on the back that is also thermally bonded to the case. So in theory, that's the most efficient installation. And we're going to try the other 2 installation methods with my KX3, which is on the right. The setup is going to be basically keying the radio down into a dummy load CW at 10 watts in 20 meters. And we're doing that by using basically a shorted cable that we will push into the radios at the same time. We're going to compare the PA temperatures. One thing I wish we could do is I really wish we could examine oscillator drift in this particular test, but today we're really only trying to measure thermal performance. So let's get started. So taking a close look at the heatsink itself, the overall thickness of this heatsink is 5/8 of an inch. So if we pull back and kind of look at Gerald's radio here, you see it doesn't really add all that much to the back of the radio considering the capability it's giving you. So 5/8 of an inch thick overall. The depth of the fins is 3/8 of an inch. It has the same holes drilled out that you have for the factory ones. And on the back you see they've left bare metal for thermally bonding to the case. Now, one thing to point out is in the package they include the mounting screws as well as a small container of thermal paste. And it's important to use their screws because this metal is thicker than the stock heatsink that comes with the KX3. The longest screw that's included in here is actually used to go into the radio and pass through the roofing filter assembly into what it screws into. So it's different than the other 3 screws in the package. So we've tried to make sure that everything is as identical as possible in these test conditions. We're actually out in a garage in an ambient temperature that's over 80 degrees with a little bit of humidity. We've let the radio sit in this area to kind of acclimate to the thing. Here, KF5JNU's radio with the heatsink, we're starting at 28 degrees Celsius and on 14060. And looking at my radio with the stock heatsink, we're also at 28 degrees Celsius on 14060. Now both radios, as I said, are connected into dummy loads. We have the radios set up for 10 watts, and we're going to be using the CW mode. And we have the radio set up to use a straight key, and we built cables that will basically short the radios out. I'm sorry, the connectors out for the CW key so that it will basically just transmit until the radio shuts down. So let's get started with the test. All right, we're going to get the test started now in 3, 2, 1. We set the radios up so that they intentionally have different tones. And if we zoom in, one thing hopefully you can see a little bit better on this one. So at 10 watts and 20 meters into a dummy load, the radio is only drawing 2 amps. My power meter has fallen over, but you can still kind of tell. So yeah, the radio is drawing 2 amps of power, and we've already seen the primary on mine go up to 44 degrees Celsius, the PA temperature, and over here we're at 42 degrees Celsius, just in this test. So it is certainly lagging a little bit behind. This is the unmodified radio here to the side. We'll just sit there and watch it climb a little bit. So I'm now at 47 degrees Celsius in the untreated radio, and we're holding at 45 on the heat-sinked radio. So it is trailing by 2 degrees Celsius. Going back, we were at 45, now we are at 48 on the untreated radio. And going back, still at 45. I'm going to focus on the unmodded radio, which just hit 50. I don't have it on screen right now, but I can tell you the other radio with the heatsink has only reached 46, so that may actually be a thermal ceiling that we've introduced. So we're at 50 degrees Celsius now. And coming back over here, we're at 47. So you can definitely see that once the heat gets to a certain point, the heatsink is certainly making a significant difference of about 4 degrees at the top end. We're at 51 now. I actually don't know where the shutoff point is. So we'll see. We're at 52. And on this side, we're at 48. So I think overall, we can stop this part of the test because we're showing that there's about a 4-degree lag with the heatsink. All right, so now we're going to unplug the radios and see how quickly the transistors return to speed. So the treated one is at 49. The untreated one's at 53. KF5JNU, please go ahead and disconnect the radios. All right, over here, see, it's already dropped down to 44, 43. Actually watching the heat dissipate out, we're at 40 there, 41. All right, we've hit 40 on the radio with the third-party heatsink. Over here, interestingly enough, the heat has also dropped. We're at 42, 41. Let's wait for it to get to 40 and we'll go back. So 40 on the factory stock, 38 here. So on the way back down, in these particular value ranges, we have a 2 degrees Celsius difference between the two. So we're going to let the radio sit and cool down, and then what we will do next is install the heatsink on my radio with no thermal paste, and then basically conduct this test again. Just one more. So I'm down to 38 degrees Celsius, and we're down to 36. So yeah, about a 2-degree difference. So we're still sitting here waiting for the radios to cool down. I guess it's been about a minute or two, and I apologize, we should have timed this, but it's been about a minute or two since we stopped the transmission test. And I've got 34 degrees Celsius on the third-party heatsink radio, and 34 degrees Celsius on the factory KX3. So the radios have now returned to the same temperature, and it will be interesting if the extra thermal mass of the Pro Audio Engineering heatsink will do anything at this point, if it really only helps at the higher temperature levels. And unfortunately, I have absolutely no background in thermal dynamics whatsoever. So this is literally two guys in a garage with some very raw assumptions. So I'm not trying to claim that this is super scientific, but it is nice to try to do a side-by-side comparison. All All right, now we're going to install the heatsink. So the first step is taking the radio apart. And there you can see that I have some Eneloop double X's. And KF5JNU is removing the stock heatsink with a standard screwdriver. All right, folks, at this point, we've run the first test. We have installed the replacement heatsink on my KX3, which we'll take a look here. You'll see mine now has the same Pro Audio Engineering heatsink. At this point, there's the old one for comparison. At this point, there is no thermal paste involved. This is just attaching it, screwing it down tightly so that there's a good physical contact between the two. The radios have sat now for about 20 minutes, and for comparison, 29 degrees Celsius and 29 degrees Celsius. So the radios are starting off a little bit warmer when they started on the previous test. Point out also the radios drawing 0.18 amps, 0.2 amps. So at this point, we're going to go ahead and start the same test again. As a reminder, 10 watts each radio, using a shorted audio cable to simulate a key down for CW into small dummy loads. And let's go ahead and get set up for that. All right, so at this point we have installed the Pro Audio Engineering heatsink on my KX3, as you can see here. We've let the radio sit for over 20 minutes now, and it's also gotten a little warmer outside, so the radios are both now sitting at 30 degrees Celsius. Here is the old heatsink for comparison. So now that we've got this on, remember there's no thermal compound thermally coupling the heatsink to my radio, and again, the radio on the left still has the full thermal bonding treatment for the PA. So let's go ahead and let the test get started again. Reminder, 10 watts, full key down into a dummy load. All right, so immediately on the fully bonding one, we're at 35, 36. On mine, we're at 36, 37. So interestingly, 38. I'm actually going to zoom out wide. I don't know if this will be visible. Now, I don't know if this will be visible on screen. But just looking here, they're the same. I can tell you I'm looking at both radios right now off to the side of the camera, and they're both the same temperature. And actually they're almost incrementing at the exact same spots. So we're at 42 on both radios, 43 on the right, 43 on the left. This is actually pretty interesting. Still sitting at 43. I'm 44 on the right, 43. That's amazing. They actually are pretty much incrementing temperatures at the exact same spots. Both 40, there we go, 45. All right, 45 on the left. Just to zoom in so you guys can see what I'm talking about. So we're at 45 degrees Celsius on the fully bonded radio, and, focus, 45 degrees on just attaching the new heatsink. Zoom out a little bit more, maybe it'll help focus. 45 both radios. 45 both radios. So that's quite interesting. We just incremented to 46 on both of them, and I promise you they are not in any way connected. All right, 47 on the right, 47 on the left. This is the fully bonded radio here on the left, and over here this is the not bonded radio on the right. So now one thing, I'll make this commentary, but until I go back and actually watch these videos, because I don't have a timer on me, and I should have had one, but I'll be able to tell from the videos how much time, but I feel like we're already getting even more running time out of this test, and I'll say that for both radios. Because remember, when we did this previously, there was a 4°C gap between the unmodified Elecraft radio and the modified Elecraft radio, and now I'm at 49 on the left and 49 on the right. So these results are actually implying that there is no need for me to even attempt applying thermal compound, which is good because thermal compound makes a mess of everything. So we're at 50 on the left, and we're at 50, focus. Sorry, I apologize for the focus problems. We are at 50 on the right. So yeah, even getting the bench grinder out and removing the coating from the case appears to be unnecessary. But KF5JNU does make a point that it's a testament to how good the coating is on these, because sandpaper wouldn't do it, steel will. No other traditional low-grade abrasives were able to remove the coating on the case. We're at 51 each. So we'll let it climb back up to 53 because that's what we did last time, but I don't think that we're going to do a third iteration. I think we have already demonstrated that we have a significant impact just simply adding the better heatsink, and there's really no need to do the full treatment. Now, I will say the next time we get together to do one of these tests, we will focus on the oscillator temperatures and then see if there's anything we can do to, well, this is interesting. The radio on the left actually just got hotter than the radio on the right. We're at 52 degrees centigrade on the radio on the right, and now we're at 52 on here, so we're back at parity. But the untreated third-party heatsink radio actually just outperformed the full treatment. We'll let it keep going here a little bit. Do a wide shot. But yeah, we'll do other tests where we try to actually measure the impact on the drift. Because one thing, I don't think I said this in the beginning, I apologize. Neither one of these radios have been temperature compensated calibration. These are straight from the factory. So we're still here. I'll go back to the left radio because it now seems to actually be heating up a little bit faster. So we'll let it get to 54. You know, and by the way, we're sitting here talking, and for a JT65 transmission, you know, the thing's only running for 50 seconds. So we have far exceeded that performance requirement to be able to do that successfully. So we're at 54 on the left. If I quickly hurry to the right, you'll see we're still at 53. So in point of fact, the radio on the right is now actually performing better. But I'm not going to say it's conclusively better and that there's no value in doing it the full way. We're at 54 there. We're 54 here. I think we're going to go ahead and pop the cables out and stop the test. So there you have it, folks. At least from our samples, which my radio serial number is somewhere in the upper 1000s. So we're at 46 here, 45. Let's see the rate of dropping with this. So they're even kind of in sync here. But yeah, the radio on the right has a serial number in the upper 1000s. The radio on the left has a serial number in the mid 6000s. And at least for these two sample radios, it looks like there is little to no benefit to doing all the work that involves thermally bonding the PAs. So I think I owe Elecraft a small apology when I made the comment at the beginning of this video that I wish that they would do that from the factory. So we're now at 42 on the left, 41 on the right. So yeah, there you have it, folks. So the definite takeaway from all of this is that it is absolutely worth purchasing a third-party heatsink. And again, we recommend the one from the Pro Audio Engineering. One thing we didn't really show is there's a little groove in the heatsink that allows it to be still fully compatible with the KX3 Lexan cover from the Sidekicks folks. We'll put links in the show notes, or I'm sorry, the episode notes below, as always. And thank you very much for watching. 40 and focus. I think it says 39. Yeah, so thanks folks. 73 from KF7IJZ.